Thank you for the introduction. As Florian said, my name is Yongshan. I'm in the computer science department. So I think about quantum computing mostly from the computing side. But today, we're going to talk about how to protect quantum information and doing computation in the noisy world. We'll start with some small tricks and trying to solve this problem of detecting and correcting quantum errors and building our ways up to in my opinion, one of the most beautiful theories in quantum in modern physics and information theory. That is the theory of quantum error correction. Not just with tricks, hopefully today we'll also have the introduction to the structure and symmetry that's used in protecting quantum information. So let's dive in. Quantum computers promises to process information in the Hilbert space, offering elegant algorithms and exponential speedups, but there's a catch, right? Quantum states are really fragile, and they decay, drift, crosstalk, they interact with the environment. The goal of quantum error correction is really boils down to how do you fight against decoherence of qubits, and while you're at it, compute a few things. So let's first talk about what can go wrong to a qubit. So on paper, a qubit is pure in an ideal superposition state, alpha 0 plus beta 1 for a single qubit. But in the lab, it's a different story. There are so many ways a qubit can go wrong. Qubit decohere, as I said, qubit decohere, crosstalk, interact with the environment. But we'd like to also try to get a clear knowledge of what kind of error could occur to a qubit. So here I list several examples of things that can go wrong with a qubit. So let's start with something that's more classical. I think we heard about classical errors and error correction from Steve's lecture before this. So let's start with something similar, like a bit flip or X type of error that map 0 to 1 and 1 to 0. So a superposition of state maps to a different superposition with the 0 and 1 flipped. That's our bit flip. There's something unique about quantum states. That's the relative phase between the two basis states. So error can go wrong like a phase flip or a Z-type error that map 0 to 0 itself, but 1 to negative 1. So adding a negative sign to it also changes the state. These are sort of more like a flip error in the quantum states that's more digital or discretized. But quantum error can be more continuous or more or less analog. You can have slight perturbation of the relative phase between alpha and beta. For example, in this equation, you can experience a rotation about the z-axis to the quantum states, which introduces a relative phase difference of e to the I delta between 0 and 1, and for a very small delta. Right? So you can really have infinite different ways of going wrong by choosing the different delta. So that's the analog nature of quantum errors. There's also probabilistic nature to quantum errors. You can experience some probabilistic mixture of errors. For example, with probability 1 minus p, nothing happens. With probability p, it completely destroys the quantum state into what we call a maximally mixed state. So remove all information in it. I over 2 essentially is a random bit. 50% 0, 50% 1. Remove all the information in it. So this process is called depolarizing. You can also experience a random Z type of error. So a channel called defacing. It can be written as nothing happens with probability 1 minus p, but apply a Z flip to the quantum state with probability p. And in real experiment, you can actually have probabilistic mixture of all the above noise. And this is all I'm listing here is some simple single qubit errors, and you can also have correlated join error between multiple qubits. So the ways that the qubit can go wrong is really infinite. And we'll, of course, get to this a bit more later, but also I see from the course agenda that you talk about more realistic noise models for special qubits, such as cat qubits or erasure qubits in later days of the lecture series. But in general, a quantum error can be described as some kind of linear map of the density operator of the quantum state. This is the operator sum representation, but the intuitive understanding is that you have a quantum state rho. The action of the error is like multiplying a linear operator or a matrix EK to this quantum state with some probability. Okay, so this is some kind of generic description of anything that can go wrong with the qubit. So it's very difficult, it turns out, in physics labs to completely avoid these errors, to isolate the qubits that well. So the question I want to ask is, can we detect or correct them? There's certainly a strong motivations for suppressing errors, because if you're given a quantum algorithm and that consists of many qubits and many operations or gates on them, there are so many ways that the qubit error, there are so many places an error can occur, and they all happen, for example, randomly or probabilistically. Let's say an error that could happen at the rate parameter p, and if you look at all the possible locations of error can occur, suppose the circuit, the quantum circuit, has size m, then the probability that none of the error occurred in the circuit decays exponentially with the size of the circuit. So in practice, if you have an algorithm that uses, for example, hundreds or thousands of qubits involving thousands or even millions of gates, you really want the error rate per gate to be really, really low. So we certainly want to suppress these errors by detecting and correcting them so that we can reliably compute in the presence of these noise. Okay, so how do we do that? We, of course, want to take inspiration from classical error correction. But the outlook might seem a little bleak at first. So here I list several reasons why we think quantum error correction is hard. Thanks to Steve, we learned about classical error correction and how effective it can be. But this boils down to some principles of classical error correction, that you can encode information or copy information redundantly via repetition. And by checking the majority or parity of the multiple locations that you store the information, you can sort of tell where error occurred. You can localize them and detect them and correct them. So let's try to take these general idea and apply to quantum states. It doesn't look so easy because, as we said, there are more errors in the quantum world. In particular, there are errors that are analog. You can have maybe a tiny bit of rotation of errors, and you don't want to sort of learn that you have experienced this error, but destroying the quantum state as well. You have to detect error without destroying it. And second, you cannot make backup copies of quantum state because of the no cloning theorem. Directly looking at the state by measuring it actually destroys it, collapses the quantum state. So if you really want to do computation on it, you want to learn about the error, not about the state. And furthermore, because quantum errors occur at a much higher rate, you have to also detect and remove errors at a much higher rate. So these are sort of the challenges that we face when we think about error correction in the quantum world. So can the qubits really be saved? The answer is yes, and the solution is also strongly inspired by classical error correction, but you have to have a few ingredients to make it work. The basic idea is still to encode information redundantly across multiple qubits, but the qubits has to stay in some kind of highly entangled states. So that we can, for example, if there's an error occurring on one of the qubits, through some kind of entangled state, the neighboring qubits will be able to help and flag such errors and try to fix it. It's like collectively they can identify the mistakes or errors. It's like a neighborhood watch. So everybody has to work together. Help each other out, making sure that collectively the information are intact, even though you have experienced local errors. Okay, so that's the sort of the theme. So let's dive into an example to see how this works. So I think this is going to first be a quick recap from what Steve talked about using repetition codes to correct bit flip errors. And we'll build up this technique to a more general theory of stabilizer codes. So let's start with this example of encoding quantum information in an entangled state. Inspired by the 3-bit repetition codes, we can actually copy the bits along each basis states, not copying the entire unknown qubit of replicas, but entangled states like this, alpha 0, 0, 0 plus beta 1, 1. And it's simple to construct using, for example, two fresh ancilla qubits, helper qubits, and two CNOT gates. Now if an error, for example, a bit flip error, occurred to the first qubit that maps 0 to 1 and 1 to 0, the state will become alpha 1, 0, 0 plus beta 0, 1, 1. And if somehow we can check if all bits are the same along each basis, we can tell, right? That's like what a classical error correction is trying to do. So can we really check if the bits are the same? The answer is yes, and the powerful technique that we're going to use is called the projective measurements. And it's quite simple. Basically, you have this data qubit set up this way for the entangled states. And we're going to just try to use ancilla qubits to check if two qubits are in the same state or a different state. By a series of CNOT gates. You know, CNOT gates will negate the target if the control is 1 and do nothing if it's 0. If you have the pair of CNOT gates laid out this way, you'll exactly flip the ancilla qubit. If the data qubit 1 and data qubit 2 are both 0, or these two gates do nothing. If they are both 1, you'll flip the target ancilla qubit twice, but flipping it twice is exactly doing nothing. But if exactly one of the qubit is 1 and the other is 0, then my ancilla qubit will be also in a state of 1. So this ancilla qubit serves as a monitor of whether these two qubits are the same or different. Now, if you look at the other pair of qubits and then check if they are the same or different using another ancilla qubits, you can actually use the 2 bits information of whether qubit 1, 2 are the same and whether 2, 3 are the same to deduce whether all 3 bits are the same or not. Okay, so well, that's a little bit abstract, but let's maybe take some examples in. And also, this example will motivate the stabilizer formalism of understanding Pauli type of errors. So as I said, suppose the first qubit experienced an X error. We can actually also try to see what does the measurement result, how does the measurement results change in the presence of this X error by propagating this X through the multiple CNOT gates. And we can, of course, follow some of the rules of commutation relations of gates. For example, if I have an X gate before the control NOT, where the X happens on the control qubit, this is equivalent to having the control NOT apply first, and an X gate acting on both the control and the target. This is directly followed from the definition of the control NOT. And of course, we can do similar things to understand how error propagates through a target qubit. Because this is control on the second qubit and negate the first qubit if the second qubit is 1, negating it is not negating it before it does not change the fact that it's negating by itself. So it doesn't matter which order you apply them. So this directly propagates through the target. By using these two equivalences, we can actually try to see how the X error propagated through the circuit. And through this step-by-step animation, I hope you can clearly see that the X is going to propagate to 2 qubits, and then this line directly propagate through the target so that this measurement will be flagged. It will be flipped, and measurement outcome is going to be 1 instead of 0. Things will be a little bit more complicated if you look at the second qubit experiencing an X error because multiple CNOT gates acting on them. And we can see that first propagate through the this CNOT. And this X error also has to propagate to the target. So both qubits will be measured 1. So you see, depending on where the error occurred, you will observe different measurement outcome. That's like the signs or the syndrome of your errors. Okay, and one final example. Suppose I have 2 errors occurring simultaneously to the qubit 2 and qubit 3. I'm going to do the same trick in propagating the X error through the CNOTs. First, for the X error on qubit 2, it will propagate all the way to the end. However, this third qubit also experienced an error, so let's do that as well. And you should have an X here and X here. Notice that you already had an X, so that actually cancels out with the other X error. So at the end, you actually only observe a flag in the first measurement result. And notice that this measurement result is the same as the first measurement result. So however, they experience different errors. So in other words, this circuit cannot distinguish between this error or this error, these 2 errors. You can get confused by just looking at the measurement results. Okay, so we can ask how many errors can this code fix? Well, if you restrict to a single error, so no scenarios 3, you only look at the single error that could happen to the 3 qubits, then we can uniquely identify where the error occurred by looking at the different patterns of measurement results. So we call the set of errors of a single qubit X error the correctable error of this syndrome circuit. And if you allow error like double error to occur in the circuit, then sometimes you get confused, but of course you can still detect it. I know error occurred, but could be either scenario 1 or scenario 3, but nonetheless, I have detected it. That's why we call this family of error detectable error, but not correctable. Okay, so this is basically a warm-up for quantum error correction codes. But of course, you can do the same thing, as I believe Steve has also shown, that you can use the same trick, modifying slightly, to detect or correct phase flip error as well. So the idea is to encode it in a different basis and do different checks such that the error propagation of Z follows similarly as we analyzed in the previous slide. And in fact, all I did here is to replace the circuit and replace the X with the Z. So the way that Z error propagate through the C0 is very similar. In particular, if you reverse the ordering, they are exactly the same. So you can see the same measurement outcome pattern as we saw in the previous slide. And again, we can identify the correctable errors as the single qubit phase flips and the detectable errors as single or double Z flips. Okay? All right. As I said in the beginning, these are not the only errors that we want to correct or detect or correct in quantum setting. What about more analog errors? What about continuous rotations? So the definition of a rotation, for example, on the first qubit about the z-axis, can be written as a linear combination of doing nothing identity or a z-flip on the second, z-flip in the second term of the superposition. But it's in a linear combination. And the weights of the linear combination depends on the rotation angle. Okay, so let's take the same circuit coming from the circuit for correcting phase flip errors, the complete Z flips. Now try to see how does it work for Z basis rotations. So what I'm going to do is to take the same circuit but put a slight rotation about the z-axis on the first qubit. I can quickly see that there's some irrelevant checks that does not check qubit 1, so let's remove that for simplicity. I'm going to analyze by walking through how the states evolve over time in the circuit to convince you that this is working. So what I'm going to do is actually more stronger than just this example at first. So I'm going to call this whole quantum state that experienced the rotation the quantum state psi. So at time step 1, you have your plus state because of the Hadamard gate, tensor with the psi, quantum state psi. And the action of the two C0 gates can be written in the two bases. If it's 0, it does nothing. If it's 1, if the control is 1, I'm going to negate both the qubit 1 and qubit 2. So that's the x1, x2 on the target qubit. Another Hadamard gate happens after the C0s. So technically, my dashed line should be after the Hadamard. So that's a little typo. So after the Hadamard gate, I map the 0 to the plus, 1 to the minus states. I can do a simple rewriting or expanding the plus to 0, 1, minus to 0, minus 1, and of course rewriting it, and we get this. By regrouping the first qubit in the 0 state with some other state, and 1 tensor with some other state, we know that if the first qubit is measured 0, we collapse the quantum state into this component. If the ancilla qubit measured 1, we collapse the quantum state into this component. Okay, so that's easier for us to now see what's the action of this whole circuit, including the measurement, to my data qubits. I'm just going to look at this term or this term, depending on the measurement result. Now let's take a closer look at what the quantum state psi is. So let's start with the ideal encoded state, applying the rotation on it. That's exactly what I did here. and expanding it to the different bases, you'll notice that I annotated here that this is exactly the ideal state, or the +1 eigenstate of x1, x2. By that I mean if you apply x1, x2, the bit flips of the first two qubits, it does not change the quantum state. Okay, so x1, x2 acting on this state remain the same. And then another term left over in this superposition is the -1 eigenstate of x1, x2. So if you apply x1, x2 to this state, you're going to get a minus sign in front of it. In other words, if you look closer enough to this, this is essentially the error state if you experienced a z flip in the first qubit, right? Okay, so that's nice. We have grouped into a superposition of logical state, ideal state, plus an error state or a z flip state. So that's like a superposition of the phase flip errors or no errors. Upon measurement of the ancilla qubits, I know I will perform this action, which is a projector, on my state psi, or this action on my state psi. Because x1, x2 is a +1 eigenstate, that acts just the same way as an identity on it. So this action actually does nothing to my ideal state. But this is a -1 eigenstate, which means that it will introduce a minus sign that cancels out with what I did with the identity. So if you have this action on this component, it cancels out. So this action on the entire state basically projects your superposition into one of the bases. And that's what we want too, because this is the ideal state that we wanted. So the collapsing helps us projecting back to the ideal state. There was a question.
Yeah, so x1, x2, is that two x flips?
Right. X flip on, I should specify the subscript is the index of the qubit. So it's an x flip on qubit 1, x2 is the x flip on qubit 2. So it is two x flip, but acting on two different qubits.
Okay.
So the summary is that if you observe 0 in the measurement result, we actually collapse the superposition into the first term, which is the ideal state that we are happy with. If you measured 1, you're going to look at the action of I minus x1, x2 over 2, and it will collapse to this component of the quantum state, which is the error state. But that's okay. This is the one z-flip, single z-flip error that we know how to correct by looking at the different syndrome patterns from the previous slide. So with upon measuring 1, we collapse to this single z-flip error state. So you can see that this circuit can also discretize errors, right? We started with some analog error. That's a superposition or continuous rotation error. But now it's a probability mixture of no error versus single z-flip errors. And then we can correct the z-flip error just as we did in the previous slide for a z-flip. Very nice. So the power of projective measurement is already revealing that you can not only identify errors if you are clever about which qubits to check, but also discretize analog errors. Okay, so you might ask, what about arbitrary errors? Now, in order to understand how effective these circuits work for arbitrary quantum errors, you have to understand what arbitrary errors look like. And without getting into the technical details too much, a nice, clean way, in my opinion, to model a quantum error is to say you have your quantum system of interest that we call the principal system. There's an environment that can potentially entangle accidentally, and It's also a quantum system, and you can use the system environment model to understand what could possibly occur to your system qubit. A simple example, if you start with a single qubit for your principal system of interest, alpha 0 plus beta 1, you can model your environment as another qubit that you don't have control over, but it accidentally entangle or interact with my system. And then because you don't have control over the environment qubit, you can model it as some kind of measurement of the environment without telling you the measurement result. So it actually is the most general form of what could happen to your quantum system. And the nice thing about this model is that it allows us to understand why Pauli operators form a complete basis. So they are sufficient for us to understand how to correct. So it's sufficient to understand how to correct Pauli type of errors so that they can be generalized to generic errors. Okay, so to see how this generic process could be modeled as a combination of Pauli errors, we can use this simple example for illustration that there's a process of U, some kind of unknown unitary operation between the system and environment that act on my qubits. And because the unitary U could map my, for example, 0 basis to any quantum states, but I can group them into, for example, 0 with some quantum state on the environment qubit that we don't care about, plus 1 tensor with the environment qubit that we don't care about. Same thing for the other basis. It can map 1 to a linear combination of 0 and 1. But the key thing to notice that it's now entangled with the environment in some state that we don't care about. So let me just write it as some generic unnormalized state phi. We can do some quick rewriting, regrouping of the terms. And trust me, this is equivalent. If you just expand the whole thing, it will match each of the 4 terms. One thing to notice for the system qubit, the first qubit before the tensor product, it's in fact a quantum state that is different from the ideal quantum state by a Pauli operator. So the first term is exactly the ideal quantum state, so identity times psi, and some junk over here for the environment that's entangled. The second term is the X-flip error that occurred to my quantum state psi. The last term, I jump over to the last term, is exactly the Z-flip error to my quantum state. And the third term is both a Z error and an X error to my quantum state. And because of the property of Pauli operators, that's exactly what happened to if you apply I times Y to the quantum state. So you can see that you can write this generic entangling operation between the system and environment as some kind of Pauli operations to my system qubit. Of course, also entangled with my environment. But as I said, because we don't have control over the environment, it's no different from tracing it out or measuring it without telling you the measurement result. This quantum state will now become a probabilistic mixture of the Pauli operator outcomes. So with some probability distribution, you'll have the no error, or bit flip error, or phase flip error, or both. Okay, so the mathematics, this is just an example, but the mathematics behind it is that the Pauli operator form a complete basis for the linear channels that we model here. So you can always write it as some kind of linear combination of Pauli operations, and upon measurement or tracing out the environment, it becomes a probabilistic mixture of Pauli errors. That gives us a good hope that by designing quantum error correction codes that are good at handling Pauli type of errors, they will work for generic errors as well. Okay, question?
I think I missed. How do we introduce the phi's on that?
This phi.
Yes.
This is, of course, me being just generic for what this quantum state could look like. But if you specify exactly what the unitary U does to my 0 state, of course, it's tensored with 0, so you can think of it as U acting on the 0, 0 basis. It's going to give you 0 if you give you a quantum state that is inside of this parenthesis. And of course, I can regroup my terms so that the 0 for the first qubit is here, and whatever left over is a linear combination of 0, 1 for the second qubit. I call that phi, but this could be unnormalized. This is not a quantum state. It's just my notation for writing whatever that is for the second qubit. It depends on which term you are, so these phi's are different. That is another way of saying they are entangled. Yeah, you can factor them out to be a product state. Okay. You can more rigorously prove this by showing the basis, complete basis fact of Pauli operators, of course. Yes, question?
So, say you have just a phase shift error. What is the usefulness of expressing it as any combination of your 4 basic operations? Is it because in the real world there isn't such a thing as just phase shift errors?
Right, so there are two questions. Mathematically, it's possible to write any error following this model as linear combination of x or z flips. But in practice, maybe you are also asking in real life, in physics labs, the type of error that happen does not follow as cleanly as just bit flip or phase flip, and they can be more analog or continuous and more random. I think maybe in the next few days you'll hear more about more realistic error models for these specific qubits. So what I'm trying to say here is the sort of a clean mathematical abstraction of errors is a linear combination or probabilistic mixture of Pauli type of operations. This is to motivate these stabilizer error correction codes that are primarily designed to correct Pauli errors. And that's for the purpose of this following lecture, I'm going to restrict to these type of errors. And the hope is that they will also generalize because this fact. Okay. All right. So what I wrote here is that, again, as a mathematical abstraction or a simplification of what generic error look like, we commonly like to analyze how quantum error correction works for a particular error model called the depolarizing channel, which is essentially saying that with probability 1 minus p, nothing happened, but with some other probabilities, you can experience an x error or z error or both error, namely the y error in your system. So that's an example of mathematically simple description of a noise channel. Okay, so let's try to understand this power of projective measurement a bit more in a sense to motivate more codes built from such structure. And they all rely on the fact of you're doing this circuit under the hood for checking errors. You have some data qubit encoded in quantum state. You have an ancilla qubit. It reads some little information out of the states. information about the error, not about the state itself, otherwise you will collapse the quantum state. So the way that they do it is to do this kind of control A operation for some operation A, and then perform measurement on the ancilla qubits. So we have already done this for the example of the two CNOT gates inside of this gadget. So I'm going to flash through the same derivation that we did, but replacing the x1, x2, which is the previous example, by a generic operation A. And then we can do the same regrouping and define some kind of projective operation, I plus A over 2, I minus A over 2, and the resulting states is either I plus A over 2 multiplying psi if the measurement is 0, or I minus A over 2 acting on psi if the measurement is 1. And yes?
So in the previous example, or as I've been understanding these, you had CNOTs in which the control was in the data and the operator was on the ancilla. And could you expand on the implications of the control being on the ancilla here?
Right. So this is the first example you are referring to, where it's sort of easier to illustrate first by saying, okay, I'm just controlling on the data and changing the ancilla. Yep. As you can see, maybe I flash it through too quickly. For the phase flip error scenario, we did this kind of circuit where we set up the ancilla and then controlled on it, target on the data. It's interesting to think about the action of CNOT gate. If there are phase errors on the data, the action is propagated to the control because Z, when you commute through the CNOT, it becomes Z on the control, Z on the target. So the flipping of the CNOT direction allow us to propagate the Z error from data to ancilla. This is actually the more intuitive understanding of my subsequent figure, where you're using some Pauli operator here to, in other words, in the context of the phase flip code, to have the phase propagated to the ancilla to the control qubit. That's called the phase kickback effect. But we're going to generalize this more to the generic Pauli errors next. But another way to answer your question about the ordering of the CNOT gate is the following fact. If you have a Hadamard gate sandwiching both sides of the control NOT gate, this is in fact equivalent to flipping the direction of the CNOTs. You can check by looking at the matrix and how they multiply. So there is another difference in the ancilla qubit of the first state, is that in this example, I did not have a Hadamard gate on my ancilla. So if you, in fact, use the same way that I formalized the control A operation, you can see that I set up a Hadamard gate here, and I can flip my the direction of my CNOTs. Of course, I can also insert Hadamard gates down here in the target. And similarly, adding another Hadamard gate before the measurement. And of course, I need to end with the Hadamard. This is equivalent to this circuit. And this will follow the same formalism I'm going to introduce. Okay, to make it more concrete, let's use a single gates as an example. Sorry. So another fact about this Pauli operator is that h times x times h is equivalent to z, meaning that my control and my C naught, this is a NOT gate, sandwiched by Hadamard, is the same as a control Z operation down here. Okay, so in other words, my circuit with the reversed C naught is equivalent to having the Hadamard in the ancilla qubit and a control Z, where Z is the target. And for detecting phase flip, it's the same Hadamard with the control X. For the bit flip, is the control Z. That's why I can generalize it to controlled A, where A is defined by Z or X. So it's I did flash through the different kind of circuits quickly, and they look different with the ordering of the C naughts, but they are actually the same type of framework of projective measurement circuits with the controlled Pauli in this form. Okay. All right, so this is a general framework for constructing, error detecting circuit. And all we need to do is to follow this recipe, but of course we have to define what our encoded quantum states into some kind of eigenstates of my Pauli operator A, so that the action of this projective measurement is to either project into the +1 eigenstates or the -1 eigenstates of the operation. So this will be easily okay. Before I talk about an example, some terminology. So in the action of A acting on some quantum state does not change it. We call that A the stabilizer of the quantum state. But in other words, the quantum state is a +1 eigenstate of the operation A. Of course, this can be better understood through an example of how this stabilizer formalism can help us describe an error detection process. So let's build a simple code out of this structure. What I'm going to show is the 4-qubit code that is capable of detecting any single qubit errors, both X and Z at once. Right? Before, we used two separate circuits for constructing bit flip or phase flip. Now it's the same quantum circuit that can detect either bit flip or phase flip. Okay, we're going to assume that the quantum state is stored, the logical information is stored across 4 physical qubits, and they are encoded in this entangled states. If you notice, these are sort of 2 Bell pairs, but they are, as you can see, spread across 4 different physical qubits that I label as 1, 2, 3, 4 in dark circles. We're going to enforce 3 checks acting on these 4 qubits, and they are defined by the operator A, right? Just replacing the box of A by this Pauli operations. Again, here the subscript under the Pauli operations are the index of the qubit that you act on. There's a nice geometric interpretation of these stabilizers and where they act on. Is if you lay out the qubit this way, in the 4 dark circles, we can see that the X type of checks is this wait for checks. So you need an ancilla qubit that interact with all 4 qubits through the control NOT operation. Another 2 sets that acting on pairs of qubits, and they are like sandwiching geometrically in this form. More explicitly, the quantum circuits that detect errors now becomes this, a sequence of checks that acts on the 4 physical qubits using 3 separate ancilla qubits. As I was saying, it all follows the same projective measurement framework where you have the ancilla prepared and apply the Hadamard operation and some kind of control A. And when A is defined by X bit flips, it's the control X, so the C naughts, and then measure the ancilla. Similarly, if you have the checks for the Z stabilizer, then you have the ancilla setup, entangle that by control Z. So this is a shorthand notation for control Z operation, acting on the corresponding qubits. And then you do that checks, 3 checks, given by the 3 stabilizers. You can, before I do that, you can quickly check that the action of the stabilizers on these encoded states are trivial, meaning that these are the eigenstates, +1 eigenstates of the stabilizers. Now going back to our warm-up example exercise, where you can identify what errors can be flagged by the measurement results of my ancilla qubits. Because of the special symmetry and the structure of the circuit, we can actually detect any single qubit X or Z flips on the 4 qubits. Okay, so as a quick example, if I have an X error on the first qubit right here before I enter the circuit, then this X error commute with the target of the C naught. So this ancilla qubit does not feel anything. It will not affect this ancilla A1. So it keeps moving, X commute through the target. But as soon as it reaches here, it's the control Z operation that will be able to flag when flip the measurement result of A2. So this measurement outcome is going to flag the X error on qubit 1. Similarly, for all the other, you'll observe different patterns. And it's detectable, not correctable, because the patterns are not unique for each error, and you can get confused among the different errors, but they are all detectable. Okay, now you want to refine our analysis further by saying that what if error happened not before my check, but during my check? Let's say an error occurred suddenly, not here, but after my first group of checks. This is called the circuit level analysis. If error could happen anywhere in the circuit, can my error detection circuit detect them effectively? Another very important question we also want to ask is, what if error happens to my ancilla qubit? What if the error detecting process itself is noisy? Right? That is reasonable too, because we're going to use noisy qubits to construct the ancilla qubit. We haven't talked at all about error that happens on the control qubits, for example, right here, the ancilla qubits. So these are all very important questions that we have to answer before we implement these protocols for error correction. But the takeaway of this slide is that by defining the stabilizers, it actually gives you a recipe for how you can correct or detect errors and construct the circuit for detecting them. It took a lot of sort of cleverness in design the symmetry and the structure of the circuit, but hopefully we will get to the formalism that allow you to construct things systematically. But let's focus on this issue of what if ancilla error has error? What if my error detecting process itself is noisy? As an example, let's see what happens if there is a X flip error on my ancilla qubit A1 at this moment in time, okay? Say between the second and the third CNOT gates of the first check. Okay, let's say an X error happens here, and according to this rule of commutation relations between X and CNOTs, we can see that it will propagate to the target qubits like that, and it also commute through the target. So there's two X flip that lingering in my circuit, and then this X error will be flagged by this CZ operation and detected by ancilla qubit A2, and this error X is going to be detected by this ancilla due to this CZ gate. So in this case, we are okay. But let's imagine the same scenario, but instead of measuring in this order, I change the ordering of which qubit I interact first. Okay, so logically it does not change anything, but it's just changing the ordering of the CNOT gate that commute with each other. But the effect of error detection actually changes. So the ordering that I'm checking now is 1, 2, 3, 4 instead of this zigzag shape of 1, 4, 2, 3. The same scenario of an X bit flip error in between the second and the third gate. Now it's not going to be detected because it's going to propagate to qubit 4 and qubit 3 on these two lines. And if we look at the subsequent error detection for X error, they belong to the same check. Okay, as I said, if two flips happens to the same check, they cancel out, and essentially propagate to. It will flip the ancilla qubit twice, so that the resulting measurement is not flagged. Okay, so this circuit does not detect this particular error, but this first circuit does. In other words, the ordering of the checks matters, and it will take a lot of analysis for designing a circuit that actually is robust to different kinds of errors. So there was a question?
You actually just answered my question.
Okay.
I was going to ask, it can detect errors, but how does it know? Can it detect which qubit it's from with certainty? And you answered it, which is it can't.
Right. So depending on the code, sometimes you can actually localize errors and identify exactly which qubit experienced an error. In that case, I can then perform a correction to it. This code is a 4-qubit error detection code, meaning that I can tell if an error occurred, but I couldn't localize or uniquely identify which qubit has the error, which prevented me from correcting that error. But of course, I can raise the flag that something was wrong in my system. So this is also the reason that my subsequent slides is going to be about how do you make more powerful codes that can correct errors or correct more errors. Okay. Okay. So this slide is actually showing that ordering of error detection matters, and it's also code specific. And for some other codes, we need extra care for defining how to do the syndrome measurements so that the noise in the error detection itself does not ruin the computation or ruin the computational states. Okay, in order to talk about more codes, I'd like to introduce this beautiful theory behind stabilizer formalism. as we were already doing, we are defining error correction or error detection codes using stabilizers. By telling you what are the stabilizers or the Pauli operators, I'm implicitly telling you how the circuits are constructed, right? Just substitute the Pauli strings into the syndrome measurement or projective measurement circuit, perform each check one by one, and you can correct for errors. So this formalism is based on Pauli stabilizers. They are constructed from Pauli operators defined by these matrices. And properties of these Pauli matrices are so nice that we can very cleanly analyze the capability or the effectiveness of error correction. To understand the power of stabilizers, let's take a closer look at this 4-qubit code and then try to generalize from there. If we look at the 4-qubit code, we know that the encoded states, I explicitly written it out, but I don't have to because I can define the encoded states as the +1 eigenstates of all my stabilizers. In other words, if I apply the gates of x, 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 x on all 4 qubits, it does nothing to my states. Or the z1, z2, it does nothing to my states. That's the definition of +1 eigenstate. But what about, and we also saw that if you have Pauli errors acting on single qubits, this will map these coerced states into -1 eigenstates, meaning that the ancilla qubit will be able to flag because the measurement result is flipped. If we look further at other possible Pauli operations on these 4 qubits, such as z1, z2, if I'm applying z gate here, z gate here, I want to understand the action of this operation on my quantum state as well. And technically, it's a 2z error, but if we apply z1, z2 on purpose, how does it change my states? Well, we can take a look at the 2 code word states and see what happens. If I apply z1, z2, it's going to introduce a minus sign if the basis states are 1 in either location. So here are 2 of them. So applying z twice cancels out the negative sign, so it doesn't change this whole state at all. Say, this doesn't change because I did nothing to qubit 3 and qubit 4. Now let's look at the negative, the second code word states. Applying z1, z2, again, introduces 2 negative signs to this basis, which cancels out, and it does nothing. So these 2 states are also +1 eigenstates of the z1, z2, and that is why I said that the action of the stabilizers, notice that this is one of the stabilizers, should not change the logical information, does not change the quantum state that you are storing. Now let's look at z2, z3. This is not something that you have in your set of stabilizers. But notice that it is actually the product of A1 and A2 and A3. Right, so if you multiply Z1, Z2, oh, sorry, this is maybe not. So I'm looking at something else. I'm looking at Z2, Z3, which is performing a Z gate on the second qubit and the third qubit. What is it doing? So if I have a z here, it's going to change this into 0, 0, -1, 1. And if I have a z3 on the first qubit here, it's going to be 0, 0 plus -1, 1 also. So this action of z2, z3 change from the first encoded state to the second encoded state, and vice versa. right? So, and notice that these two states are orthogonal. So these are the basis of my logical information. And this action is a map between the different logical bases. So what is a mapping between logical bases? Well, that's a logical operation, right? So if you want to change from a logical 0 to a logical 1, that's your logical X gate. So you can also use these Pauli operators to define how would you like to do computation on it by mapping between the basis states. That's an example of a logical Z operation. And furthermore, I can also see what happens if I apply x1, x2 to this encoded states. And let me just summarize. Through this example, we saw that there are properties of these Pauli operations. These are sort of multi-qubit Pauli operations. It tells you how to apply Pauli gates on different qubits. And they form a group, nicely form a group because multiplying x, y, z together give you another Pauli operation. They also have very nice commutation relations. Exchanging the ordering of applying x and z, for example, introduces a negative sign. So they anti-commute. So I can write down different ways a Pauli operation commute or anti-commute with each other. xi is ix, or changing xx is, of course, the same as xx. So the nice property of a Pauli operation is that they either commute or anti-commute, and exchanging the order either does nothing or adds a negative sign. Okay, so you can check for all different combination of Pauli operations this way. And then I can further group the type of Pauli operations by their action on my encoded states. So, for example, I had worked out the example of Z1, Z2 that belongs to one of the stabilizers, and we saw that the action of Z on qubit 1 and Z on qubit 2 does nothing to my encoded states. So that's essentially the identity action on my encoded states. In other words, there's no error or no change in the logical information. And you can tell because this also commutes with all the stabilizers in here. There's another set of Pauli operations. For example, let's say Z on the first qubit, as we saw, is one of the detectable error. And it's detectable because it will be flagged by one of our stabilizers, namely A1. I know that it will be flagged by A1 because the action of Z, Z1, anti-commute with my stabilizer A1. In particular, Z1 and X1 anti-commute, that's why the ancilla qubit implementing this stabilizer will be flipped in the measurement result, and serving as a flag or syndrome for that error. Okay, so furthermore, we analyzed the Z2, Z3, which commute with all my stabilizers, but it does change my logical basis information. So that acts as a logical operation or logical error. It commutes with all the stabilizers but change the code words. These are, of course, undetectable because they commute with all the stabilizers, but it allows us to map between the different encoded states. Changing logical information. So we can group the different types of Pauli operations into things depending on their commutation relations with our stabilizers. Okay, with that in mind, I'm going to now quickly introduce something called the surface code, which is essentially a larger instance of the 4-qubit code. As you can see, I'm defining the stabilizers of this new code in a similar way as I defined the 4-qubit code. Right? I'm laying out the physical qubit in a grid, in this case the 3x3 grid, and I'm performing my checks of neighboring qubits using ancilla qubits. And they follow this nice geometric layout that they are in a 2D grid checkerboard fashion. And you have this yellow checks that is the X stabilizers. In the case of this phase of the grid, it's acting on qubit 2, 3, 5, 6. So it's doing the X checks on 2, 3, 5, 6. So it's X2, X3, X5, X6. That's the stabilizer. And for a green phase of the grid, we're doing a Z-type stabilizer given by the circuit like this. So once you lay out them this way and define the X and Z type of stabilizers using this checkerboard fashion, you can, in fact, correct single bit flip or phase flip errors. The nice thing about this code is that I can draw the picture because of the 2D nearest neighbor interaction that's given by this special symmetry or geometry of the code. It's not just drawing this picture easily. This means that we can implement it more easily. For example, with superconducting circuits where you will embed these qubits in these physical locations, and the ancilla qubits that has to interact with my data can be in the middle. And all we need is a degree 4 connectivity, allow you to do the control NOT operation with its 4 neighbors, and nothing more. A3 does not have to interact with qubit 7, for example. That's nice because of the local structure. Another important feature of this surface code is that it's resilient to hook error. Recall that when we talk about ancilla errors, when ancilla qubit can have error themselves, we want to avoid the error on the ancilla qubit propagating back to my data qubit, therefore ruining my computation. This is the type of error called the hook error. And you'll notice that I did a specific ordering of the gates in order to make it work. In particular, for this X stabilizer, I'm following the same zigzag pattern that I introduced for detecting the ancilla error in the previous example. So that's the same zigzag shape. But the Z stabilizer follow another different zigzag way. So this is more or less like a capital letter N. This is a flipped version of N. So it's actually a different way that you zigzag that will allow you to detect error that occurred during the circuit on the ancilla qubit as well. Different codes will have different syndrome extraction circuit or syndrome measurement circuit, and they may or may not be resilient to hook error. Nice thing about this code is that we can find such circuit that are resilient to the hook errors. What else? We also like the code because these two circuits that acts on different qubits, sometimes they share qubits, but these can be completely running parallel. Because of the way that we starts and end the different qubits, you can actually do all the gates that I lined up in these vertical layers in parallel. For example, the bottom, you all start with the bottom right of the data qubit right here, because that's the first qubit you interact with from the ancilla qubit. For example, A2, A3 will both interact with the bottom right corner of the physical qubit, even though A3 share qubit 5 with A2, they check them in a different order, and then doing that allow you to do both checks in parallel, and then you move on to the other depending on the zigzag direction. They will not conflict. This is also really nice. Remember, we want to make sure we can detect error fast enough then they occur. So we want to make sure our circuit for detecting error is very shallow in depth, so they can be implemented in a very short amount of time. And the circuit for correcting surface code is a constant depth of 7 gates per cycle, 7 coming from the Hadamard, the 4 CNOTs, Hadamard, and the measurement. So everything is done in parallel, even though there are so many checks to be done simultaneously. Okay, so I'm basically illustrating all the different factors that you have to take into account when you evaluate the effectiveness or performance of an error correction circuit. Now let's look at the capability of correcting single qubit errors by this surface code. As I said, we can understand the error correcting capability based on depolarizing channel to begin with. They follow the nice X, Y, Z type of errors on my physical qubits. And the code words can be defined on the 9 physical qubits. It will be a mess to write down the exact state of the entangled encoded states of my 9 qubits. But thanks to the stabilizer formalism, we know it's a state that is a +1 eigenstate of all my stabilizers, right, introduced in the previous slides. So by defining the stabilizers, as I did in the picture, I'm implicitly telling you what the quantum state should be in for the entangled states of the physical qubits. And that's the +1 eigenstates of all the stabilizers, so that for every element in the stabilizer set, the action of it is trivial. Okay, so what does the process of error correction actually do? It's essentially trying to classify the different quantum states that my physical qubit could be in into some subspaces. In fact, the direct sum of several subspaces that is labeled by different stabilizer measurement results. So remember, the syndrome measurement is a projective measurement. If the measurement results return +1, I know that my quantum state is now in the +1 eigenstates. If the measurement result is -1, I know my quantum state is projected to the -1 eigenstates. And because of the syndrome measurement projection, and depending on the +-1 measurement results that's showing up in all these stabilizers, I can now classify subspaces that are +- or -1 eigenstates of each stabilizers. Okay, so I can do this simple classification, and if all the stabilizers show up +1, I know I'm in the no error case. That's the code space. So everything should start with the +1 eigenstates. That's my code words. Suppose one of the stabilizers are flagged -1, that is projected to the first error space, and we'll be able to tell what error occurred in this subspace. Something I wanted to illustrate now is that how do you know how many, what's the dimension of the logical space defined by this code word space? Okay, so something we can check is the simple dimensionality check. So in the case of physical qubits, I started with 9 physical qubits, and the entire Hilbert space is dimension 2 to the n for the 9 physical qubits. And of all the possible basis states that span the entire 2 to the n dimensional Hilbert space, some of them are +1 eigenstate of a stabilizer G. Some of them are -1 eigenstates. In fact, I will completely cut the entire Hilbert space in half. One is the +1 eigenstate group. The other is the -1 eigenstate group. And by doing this projection, I'm sort of picking one of the group. So if I had a stabilizer code defined on 9 physical qubit, that's 2 to the 9 dimension Hilbert space. And now I have 1, 2, 3, 4, all the way to 8 stabilizer checks, stabilizers, which each of them can sort of cut the space in half and group into either +1 or -1 eigenstate of that stabilizer. By defining 8 of them, I sort of picking one of the 2 to the a possible groups. In particular, the group that I said was the +1 eigenstates of all the 8 stabilizers. Right? So I have cut the dimension every time in half 8 times. And so if you look at the dimension of the the subspace that you picked, this guy, is 2 to the 9 over 2 to the 8. Okay? So that's exactly dimension 2. And that's good because a dimension 2 means that's one logical qubit. Okay? We can define one qubit is a dimensional 2 Hilbert space out of this subspace. Same thing actually for all the other error spaces. They're all dimension 2. And there are 2 to the 8 of them. Each has their unique signature of either +1 or -1 eigenstates of the stabilizers. Okay, so this is sort of a simple way of counting how many logical qubit or how many dimension you have left after this projection. We'll come back to this calculation when we define more formally the stabilizer codes. Okay, so I think this is a good time to take a break. And after the break, we will do a quick recap of what the surface code looked like and also generalize to doing computation on them. Okay, so let's get back to it. So we have defined this code that I call the surface code on 9 physical qubits. And we said that because of the 8 stabilizers that each divide the Hilbert space in half, +1 eigenstate subspace or -1 eigenstate subspace, we can define one logical qubit out of this because I have 2 dimension left in the subspace. So that's the sanity check that we have defined in error correcting codes that allow us to define the code words and checks. But to understand its power in terms of error correction capability, we will look at, again through examples, how to check for errors using this setup. Again, let's assume that we have bit flip or phase flip type of errors that could happen to any of the 9 physical qubits. Suppose I have an X error on qubit number 5 in the middle. The question is, which checks would flag this error? And notice recall from the previous slides, the definition of these codes is that the green patch defines a Z-type stabilizer. So it's Z1, Z2, Z4, Z5. And the yellow patch defines an X-type of stabilizer that is X2, X3, X5, X6, for example. And we know because of the projective measurements, when an error commutes with the stabilizers, meaning that in the error correction circuit, the syndrome measurement circuits, the error will just commute through till the end of the the circuit without the ancilla, without propagating errors to the ancilla qubits, thereby flagging it. But if the error anti-commutes with the stabilizer, it will flip the ancilla qubit and the measurement result will be able to flag them. So what we are looking for is therefore stabilizers that anti-commutes with this particular error. Okay, so due to the nice property of Pauli operators that we know, these two patches that check for Z stabilizers, because they have a Z acting on qubit number 5, and yet there was an X type of error happening on it, X and Z anti-commute, this will flip the ancilla qubit A2 and A7, and they both touch on qubit number 5. And all the other qubits are going to stay the same. And in particular, we know that if you have an error acting on qubit number 5, X5 in particular, your quantum states is now a -1 eigenstates to these two stabilizers, yet +1 eigenstates to all the remainder stabilizers. In the picture that I had from previous slides, essentially you have a X error on qubit 5 that map you from the code space to one of the error space that is -1 eigenstates to some of the stabilizers. Okay, and therefore you have two checks that raise the flags. Okay, so that's what I was trying to say. The state, even though I didn't write it down explicitly, we know is a -1 eigenstates of these two stabilizers. I should have written Z because in the X-type error and the green patch. So it's actually Z1, Z2, Z4, Z5. That's a -1 eigenstates, but +1 eigenstates of all the other stabilizers. Okay, here's another example of a Z error on qubit number 6. Again, we're going to look for stabilizers that will raise a flag, namely those that anti-commute with this Z error, and that is the X check performed on the qubit number 6, and therefore we have a flag there. Now here is a question in reverse. So if I perform my checks as I requested, and I saw two flags raised, can I guess what was the error that occurred? Because after all, the error correction process is about looking at the checking for the syndromes, see the raised flags to guess what error was occurred, and then perhaps try to correct them, right? So we don't know where was the error, but we can only look at the flags. So suppose A1, A3 both raised the flags. What could be the error that caused this? Yes?
It looks like it could be an X error because both of raised at the X-flip zones.
Okay, so recall that the yellow checks are X stabilizers.
Yeah.
Errors have to anti-commute with them in order to raise a flag.
Oh.
So
that has to be the opposite.
exactly.
Z on 2.
So it should be a Z error is set on qubit 2, and then will, because it neighbors with both checks, it will raise the 2 flags. Very good. So one possible error could be Z acting on qubit 2. Are there other possible errors that it could occur and cause this flags to raise? Yes?
Maybe Z1 and Z3?
Z1, Z3, good. Z1 raised the flag and it doesn't affect A2. Z3 raised the other flag, so that's exactly what I wrote also. That's another possibility. And then we can, of course, argue which one was more likely. Assuming that the errors are all independent, let's say, and they occur at different locations of the physical qubits, then one error is more likely than 2 consecutive errors at the same time. So we can say, okay, yes, indeed, there are multiple possible errors that could cause the flags, but the single error on qubit 2 is more likely. Okay? Identifying the most likely error is the process of decoding. Use the syndrome information, which is only partial information of what's happening, to infer what was the cause or most likely cause. So the process of decoding, as I said, is trying to figure that out. I only showed an example. As you can imagine, if I had lots of errors and lots of flags, it's going to be very complicated to check for the possible errors. And something I didn't spend much time on is that this surface code is actually generalizable to a larger number of qubits. For larger grid, for example, in this case, it's a 5 by 5 grid instead of 3 by 3 in my previous example. Using more qubits to encode still one logical qubit, you pay the cost, but you gain sort of more protection. In this case, you'll have more locations for possible errors, but you have also do more checks to try to resolve it. And just to give you a flavor of what decoding looked like in practice, taken a surface code, of course you can model that as some kind of graph. They are nearest neighbor connected. These are the sites of the ancilla qubits that could raise a flag. And then you can sort of identify the locations of errors that did raise a flag and try to solve a graph theoretical problem of where could be the errors that cause those flags. And as you were also doing in the previous slide, because an error could cause both neighbor flags to raise, you're trying to match up the 2 flags that are close to each other. So it's like a matching problem. This edge means that the data qubit sitting in between these 2 flags must have an error for both of them to raise a flag. Once you have so many flags, trying to find the matching between pairs of flags is precisely the task of identifying the error that would cause the flags. And it's an optimization problem because you want to find the most likely error. That translates to finding a match that is the minimum weight. Because indeed, I could maybe say that there are far distance flags that are matched, meaning that I believe consecutive error occurred to make that happen, and that will occur with less probability. So finding the minimum way perfect matching on this decoder graph solves the maximum likelihood decoding problem. This algorithm would work well if your errors are localized and rare. If it's actually really actively detecting error, it's going to be very confusing for the algorithm to decode. Yes?
If two errors happen around the same area, can it unset the flag?
Exactly, yes. So I think I might have it somewhere. Okay, for example, let's get back to here. If I have another X error that happens to qubit number 6, this flag is still there, but because this check interact with both qubit 5 and qubit 6 that experience the errors, they will flip the ancilla qubit twice, thereby making it back to the 0 and not raise the flag. This can also be seen by saying the X5, X6 commute with my stabilizer. That's because every qubit that has X and Z introduce a negative sign because they anti-commute, but they anti-commute twice, so the negative sign actually cancels. That is an example where the flag canceled out because of multiple errors. So then what you will be looking for is the flag that would be raised here, right? So A4 would raise the flag because it only checks qubit 6. And then I'm going to try to match this flag, A2, with A4. The only way they will be matched is by asserting that there are two errors that occurred both here and here. So there could be longer distance flags that you have to match, assuming consecutive error that happen in between. Okay, so people build software to solve this problem for even larger scale graphs, and this figure was taken from my colleagues in the Yale Computer Science. With their permission, I took this picture from their paper. They also have a software called Fusion Blossom based on the Adam's Blossom algorithm for finding minimum perfect matching, minimum way perfect matching of a graph to solve this problem efficiently. It's until you can come up with the most likely error, that is when you can maybe think about recovery. And if you can't recover the quantum state fast enough, then the error occur or decode them. It also delays the whole error detection process and also therefore impact the effectiveness of error detection. So we need to do this fast to keep up with the rate of error and the computation that occurred with it. Okay, so to formalize the whole construction, we define a surface code using the stabilizers, and they're carefully crafted in a way that it follows this geometric symmetry and very balanced checks, like checkerboard checking for each of the data qubits. We can, again, implicitly define the code word states of the 9 physical qubits in this case to be the +1 eigenstates of all the stabilizers. And if any of the if any of the stabilizers raise a flag, that means you end up in a -1 eigenstate of some stabilizers. And try to map them back to the original code word space is the recovery process. The reason that we can protect against errors is because the higher dimensional Hilbert space, namely the 9-qubit physical Hilbert space, is grouped into code word space that is spread out in the entire Hilbert space, spread out in the sense that mapping between the code word states of all the +1 eigenstates involve multiple Pauli operations on the qubits. The number of bit flips or phase flips required to map between logical code words is called the distance. In other words, if that many bit flips or phase flips happened to your code words, which map the logical 0 to logical 1, there's no way to detect them, right? So if there's fewer error than that, you are mapping it to some other states that's sort of -1 eigenstates to some stabilizers, then you can detect them. So any weight D Pauli operations could occur without triggering any syndrome. That defines the limit of which your error correction can work. How many errors can you correct? In particular, a distance D code can detect up to D-1 errors. Right? So if you are just short of mapping to another code words, you can tell because it's not a +1 eigenstates anymore. But in order to correct for the code words, you have to know which code words to get back to, and that will be lower than the code distance. In particular, it will be D-1/2. So it's shorter than halfway between the two different code words. And then you can go back to the closer one. Okay, so people define code distance to help understand the theoretical limit of how many errors this code can correct. Of course, there are other parameters to define what is a good code versus bad codes. How many physical qubits does it use? Right, that's the physical resources that we have to take. And how many logical qubits it defines. The ratio between the logical qubits and physical qubit is called the encoding rate. Right? So we're using more physical qubits to define fewer logical qubits. And of course, if you have larger encoding rate, that is more resource efficient. So we like to pick codes that with larger encoding rate. As I was doing, in order to get n physical qubits to encode k logical qubits using stabilizers, we can actually we know that there will be n minus k stabilizers, because at the end of the day, you are encoding a 2 to the k dimensional subspace inside of a 2 to the n physical Hilbert space by cutting up into +1, -1 eigenstates of the stabilizers. Every stabilizer cut the 2 to the n Hilbert space in half. If you're doing that n minus k times, that's the number of stabilizers you have. Each subspace you remain is dimension 2 to the k, allowing you to define a k logical qubits. So given a nkd codes, you know that you have to define n minus k stabilizers for it. These are really structured and has a lot of symmetry in the entire Hilbert space. That is why we can perform error correction on it. So this will only work if the code satisfies certain condition. And this condition is defined as some kind of relationship between the stabilizer projections that you do and the set of errors that could occur, right? So the checks is only good for correcting certain errors, and by matching the capability, the checks with where the error occur, you can define the family of error that can be collectively detected or corrected by a code. Mathematically, you can define that through this condition, which is the relationship between the types of errors and the projections that you do. So I'm not going to introduce the mathematical definition in depth, but to offer the intuitive interpretation of the error correction condition, or the Neal-Laflamme condition, it's in fact pretty straightforward. In order to understand if a family of error is perfectly correctable, I want to make sure that we define correctable by saying that if the quantum state you start with undergoes some error channel epsilon, hopefully your recovery, or the detection plus correction, can bring you back to the quantum state rho. This only works if your error detection done by the projection of the stabilizers satisfy the relationship with the errors E sub I in the following form. And this is not so difficult to see what it means. What I wrote here is the interpretation of it. It's essentially to say that if you have two orthogonal basis states in the code words, you want to maintain that they are orthogonal after the errors. Otherwise, they're not perfectly distinguishable. So psi k, psi l are two of the basis states in the logical Hilbert space. First, my error correction should not ruin the computation itself. So that is guaranteed by saying the projection given by the stabilizers act trivially on my logical basis states, code words. Does not change my quantum information if no error occurred. If there's some error that occurring, for example, take any two errors, it will not change the relative angle between the two code words. In other words, they remain orthogonal. Therefore, if you perform some measurement along the right basis, you can still perfectly distinguish two basis states. And again, this picture allows us to see the internal structure of this Hilbert space that we that we sort of engineered to make sure that each projection is sort of cut the space into subspaces that is recoverable, in the sense that two basis operations in the code space through some error channel that map to the error space, they remain orthogonal, so that you can still use a unitary operation to bring them back. Recall that unitary operation is sort of preserve the angle between the vectors. So if it's correctable, meaning that we can use a unitary recovery operation, the basis operation has to stay orthogonal. Okay, so this is the mathematical definition of what is correctable. What I want to end with for today's lecture is to say that it goes beyond just correcting error. Ultimately, you want to also do computation while you are performing error correction. So that is the notion of fault-tolerant computation on a code. For example, you want to use that logical qubit, prepare in some logical state, perform some logical gates, perform logical measurements, and hopefully physical errors that occur within the logical qubit is going to be detected and corrected. So in practice, the process is going to be a cycle. So you prepare the ancilla qubits, you entangle with the data, you check for errors, you measure the ancilla, raise the flags, and then reset them. And that is done for every gate, every operation, and maybe every now and then. And over, the code checks for signs of error without interrupting the computation. Okay, so that's the sort of the cycle of error correction. And just to give you a hint of how to perform computation on the defined code, we'll again resort to the stabilizer formalism, which is quite powerful for understanding what happens to our logical qubit. You can define logical Pauli operations to begin with. And it turns out that for this surface code construction, performing logical X on the qubit is implemented by physical X gate on this set of 3 qubits, 1, 5, and 9. And then Pauli Z operation acts on the other diagonal of this surface code patch, 3, 5, 7 Z operation. A quick check that you can do is that this logical operation commute with all my stabilizers. In other words, it does not change. If I perform the logical gate, it will not be accidentally identified as an error, right? It does not anti-commute with any of the stabilizers, so they will not raise a flag because of my gate. And you can do the same thing for both. And then it's also important to see that the logical Z and logical X anti-commute with each other. After all, they are Pauli operations that anti-commutes. And you can see that they anti-commute on a physical qubit of Z of qubit 5. Right? So Z5, X5 anti-commutes, thereby enforcing the whole Pauli operation to anti-commute. Okay, so this is sort of not the only definition of Pauli operations. You can define something else that satisfies these criteria. In fact, this is all you need to define the logical Pauli operation, but that's non-unique. For example, I can choose a different set of 3 qubits for the logical Z, acting on 7, 8, 9. These operations commute with all the stabilizers, but they allow you to map between code words. As I was saying in the table, we can group the stabilizers into no errors or detectable errors or logical operations. And here's an example of a logical operation. Similarly, we can define alternative X operations, logical X operations along the boundary, like that. Okay, so I'm going to briefly talk about what you need to do beyond Pauli gates, but due to the time constraints, I will not do the full description of how they are implemented on surface codes, but just to motivate that to implement universal computation, we need more than Pauli operations. And some of them are Clifford operations. And also to motivate why stabilizer formalism is so powerful, it can allow us to design Clifford operations on them too. We can recall the property of Pauli group elements, and we define stabilizers from this Pauli group. And they have properties like they commute with each other. Code words are +1 eigenstates of all the stabilizers. And the syndrome measurement circuit, the projective measurement circuits for error detection, can be modeled as projectors of the stabilizers. The question we can ask is, are there other elements that we didn't pick from the Pauli group that also commute with my stabilizers? If there are any, that means they can be defined as logical operations. Or it does nothing to the code words, then it's an identity. So we can define another group of operations called the normalizers that are elements that commute with all my stabilizers out of the Pauli group. So the other things that are not stabilizer, but they all commute. These are nice things that we can see act as a logical operation. To see how this is a logical operation, we can say that suppose my operation map the one code word to another. Then performing the stabilizers do not sort of change the fact that they will do this mapping because they commute. Okay. There are other operations that can perform operations on the code words. For example, if you define unitary acting on a code word states that is stabilized by G, if they do not commute with my stabilizers, they can also be used as a logical operation as long as they satisfy nice properties. For example, this is equivalent to sort of doing the unitary operation on the code word states and then stabilized by this new set of stabilizer. So U, G, U dagger is your new stabilizers of the codes. And these are sort of motivating example for Clifford operations that map from Pauli operations to Pauli operations. So when the new stabilizers fall back into the Pauli group, they are nicely defined. We can still use stabilizer formalism to of the Pauli group, Pauli stabilizer describe it. So if we enforce this new stabilizer to be an element of the Pauli group, we know that such unitaries are called the Clifford. An example of those gates are Hadamard gate, phase gates, and CNOT gates. So they map Pauli operation to another Pauli operation. So performing these operations and update the stabilizers, change the stabilizers back into Paulis are nice properties of these gates. But however, we have to say that these do not form a universal set of gates in the sense that if you start off with a 0 state and perform only Clifford gates or Pauli gates on these quantum states, you do not get to, for example, only the single qubit ones. Right? So this is a block sphere for the single qubit. Start with a 0, perform Pauli gates or Hadamard or S gates. It does not get you anywhere on the block sphere. It gets you only certain points along the block sphere. For example, an X gate jump back to 1, and then a Hadamard gate get to plus, and so on. So if you have probabilistic mixture of these Clifford gates, it gets you to the interior of this octahedron, this stacked pyramid shape. So not everywhere inside of the block sphere, but those enclosed by this octahedron. This is not universal. In order to get to densely everywhere on the block sphere or interior of the block sphere, we need another gate that is not Clifford gates. So I think I'm going to show you, flash through some of the construction of Clifford gates and the basic idea of non-Clifford gates to show that surface code as a promising example of enabling universal fault-tolerant computation. So by defining Clifford gates such as Hadamard gates and phase gates and CNOT gates, we can construct all the Clifford states. So it turns out if you want to map between the eigenstates of X, logical X and logical Z, because of the symmetry of all the 9 physical qubits, applying the Hadamard gates on each of the physical gates allow you to construct the logical header mark. That is to say, if I have a logical X on 159, because I applied header mark gate on 159, it turns into a logical Z. And that's exactly what my logical Z is. So that's also exactly how I want my logical header mark to perform, to map between logical X and Z. So physical header mark on 9 qubits suffices. There's a catch, of course. You have to, if you apply the header mark gate, it's equivalent to flip the X stabilizers to the Z stabilizers, so the colors you see are changed. So in order to preserve this structure, it's simply rotated by 90 degrees. So it's header mark gate up to some rotation. So that's a way to implement header mark gate. And same logic follows for control NOT gate. In fact, if you do control NOT between the control logical qubit and target logical qubit, you simply perform C-NOT gate of each of the physical qubit respectively. So control on qubit 1, target on qubit 1, each on the logical qubits, and then pairwise for everything, implement the logical C-NOT. I'm describing the results, but you can actually verify it from the logical stabilizers and how that is transformed by the set of physical gates. But as you see, that require lots of gates that are not easy to implement or draw in the 2D. You have to implement the long remote gates and pairwise. So people have also thought about using other helping qubits to require less connectivity. So you can use additional logical qubit and interact only in nearest neighbor physical qubits to implement the logical operation. And this is called the lattice surgery. Through this, we have already discussed its transversal gate set of the surface code, but it does not give you all the universal operations that you wanted. In fact, there is a no-go theorem saying that no quantum error correction codes can implement a universal gate set with only transversal gates implementation like this. So in order to circumvent this but still be able to perform universal computation, you have to circumvent it with other techniques. And I'm not going to talk too much in detail, but the idea to circumvent this non-Clifford gate implementation is through teleportation. And the takeaway is that you can construct, maybe the next slide is better, you can construct a Clifford circuit that you know how to implement fault-tolerantly with transversal operation, plus some initial quantum states that we call sort of magic states. Once you get hands on such prepared magic states with high fidelity, we know Clifford gates can be performed fault-tolerantly. Then the logical operation of the non-Clifford operation can be performed with high fidelity. It's sort of shifting the difficulty of performing a logical T-gate into preparing a special resource states. And that is relatively easier because you can, for example, employ post-selection or trial and error to prepare lots of states and only pick the high fidelity ones. So that's a sort of a better route than directly implementing the logical gates. Okay, so with that, I'm going to end here and leave this page up, and then say that this is sort of one proposal for scaling up quantum computation by error correction using surface code. In order to perform computation on it, of course, we have to carefully think about implementing the logical operations while performing error correction. And so everything nicely fitting to this stabilizer formalism that we introduced, leveraging the properties of Pauli operations and Pauli group. This has proliferated into a research field of using the stabilizer formalism to define new codes that is capable of correcting more errors with fewer resource elements, and maybe enable logical operations with more with cheaper operations. And hopefully this lecture allow you to sort of tap into this nice formalism so that you can understand these more advanced constructions. So with that, thank you for your attention, and leave this slide up for sort of a different code that people designed, but still using the stabilizer formalism. And I hope after this lecture you will be able to join this effort of discovering new codes and inventing new protocols for helping us reaching fault-tolerant quantum computation. So thank you.